Good day, everyone. My name is Ting Dai. I am from IBM Research. I'm presenting the work called Automatically Detecting Risky Scripts in Infrastructure Code. This is a joint work with Alexei, Gregos, and Sai. Modern IAC tools have their own programming paradigm to write infrastructure code. For example, YAML for Ansible playbooks and Ruby for Chef cookbooks. They also support embedded scripting languages such as Shell and PowerShell to either manage the infrastructure resources like operating systems, storage, and networks, or interact with applications to execute the automation procedures. Risky patterns in infrastructure scripts introduce bugs and expose vulnerabilities, which lead to widespread of business disruptions, application performance degradations, and leaving infrastructure with vulnerabilities. Example risky scripts such as remove partition drive letter C, which removes the disk drive, could result in business disruption when they are invoked in the production environment. Unfortunately, different from traditional software programs like Java and C, C++, which are equipped with mature bug and vulnerability detection, testing, and verification tools. Existing techniques and practices for checking risky IAC embedded scripts are rudimentary. It gets more challenging when the modern code development shifts to the community-based approach where a team of contributors have mixed skills, experiences, and responsibilities. Particularly, most contributors are system administrators who lack the same level of understanding and debugging support compared with software developers. Studies have shown that nearly 75% of system downtime is caused by human errors, and many service outage incidents are caused by mistakes made by the system administrators. For example, in 2017, the Amazon S3 service became unavailable due to a removal command invoked by a system administrator who inadvertently removed a large set of servers, affecting other AWS services that rely on S3 for storage. This service disruption lasted for 5 hours with financial loss of $150 million. A recent Stack Overflow post draws a lot of attention where the developer accidentally deleted the whole database and file system because this developer mistakenly used the double slash rather than the pound as a command symbol in a shell script where a rm-rf command is invoked. Existing infrastructure linters such as Ansible Lint and PuppetLint lack the capability of checking IAC embedded scripts, while generic script analyzers such as Shellcheck and PS Script Analyzer report issues in the scripts by checking their formats and syntaxes, which has brought to light the opportunity of conducting static checking over the IAC embedded scripts. However, applying the existing generic script analyzers directly on checking infrastructure code can result in both false positives and false negatives. Moreover, without correlating the identified issues with their risky behaviors, users have no understanding about how the risks manifest in the production environment, what the potential business consequences of those risks have, and how severe those negative consequences are. Bridging the gap between generic script analyzers and business consequence in order to deliver a robust and accurate checking framework gives us the opportunity and motivates our work. We propose an analysis framework which takes an infrastructure code repository as input. It first generates structure representation trees for the repository. By traversing each structure representation tree, it composes script contents by removing template renderings after identifying that the infrastructure code involves script executions. After parsing the composed scripts to script analyzers, it receives the checking results with issue IDs and the line numbers of the composed scripts where the issues reside. To satisfy configurable business compliance requirements, it assigns the severity level and potential impact for each identified issue based on predefined assignment rules retrieved from the knowledge base. It then maps those issues to the corresponding infrastructure source code lines before returning them back to the user. The right-hand side of this slide shows an infrastructure code example, including the Ansible playbook directory and a shell command invoked inside the playbook. The left-hand side shows a structural representation tree of the infrastructure code. Starting from the entry node, each node contains multiple components. A component consists of multiple units. A unit indicates variable configurations or represents business logic operations. An operation uses static configured variables, while a variable can be assigned with the value of an operation's runtime output. A structural representation tree is a tree data structure to represent the syntax abstractions of the infrastructure code. It helps to extract and organize the key information in the infrastructure code and exclude details in order to ease the process of accurate script extraction. The top-down sequential order of the structural representation tree guarantees both the reference of defined policy between variables and operations, and also the happens before relationships among different operations. Modern IAC platforms provide their own programming paradigm, syntax, and libraries to support script invocations. For example, Ansible's command, shell, Windshell modulus, chefs execute, script, bash resources, Puppet's execute resource, and Terraform's local execute and remote execute provisioners. To detect whether the infrastructure code invokes scripts, we traverse the generated structural representation trees, obtain their leaf nodes, and check whether the operation leaf nodes use the aforementioned script-related IAC libraries. In this example, we see that at line 24, the Ansible shell modular is identified by the script detection. The script composition is a process of replacing a template variable in raw scripts with its value extracted from the variable map. We recursively conduct the replacement until all the referenced variables are replaced by their defined values, or until the script cannot be further composed. For example, from step 0 to step 1, we extract the value of the TSMID and TSMPath variables and get the composed script. The composed script may still contain template variables which are undefined in the infrastructure code. Passing those syntactically problematic scripts to script analyzers results in inaccuracy and false positives. To remove the template rendering from the composed scripts while still preserving the variable reference, we reformat those template variables in correct script syntax. In this example, we reformat the shell script by replacing the double braces with the dollar symbol. To advocate the top-down sequential order of the structural representation trees, the variable map initially contains all the statically configured variables. It then gets in-time update with the variables which are assigned by operations execution results. The initialization and in-time update of the variable map guarantees the defined reference order in two aspects. First, the statically configured variables can be accessed by all the operations. Second, dynamically defined variables can only be accessed by the later operations. For example, any operation cannot access variable 3 before time t1. The in-time update handles lexical scope variables by overriding the old value with the new value. For example, after time t2, variable 2 is updated to variable 2 prime. To satisfy business compliance requirements, our analysis system regulates the identified issues with impact categorization and severity assignment. We conduct an empirical study on the existing script analysis rule sets, including 345 rules from SureCheck and 64 rules from PS Script Analyzer. We study the code patterns checked by each rule to identify what risky behaviors and consequent negative impacts the problematic code can have. We categorize the issues based on the potential impacts as non-issues, security vulnerabilities, availability issues, performance issues, or reliability issues. We assign the non-risk issues severity level as low, security and availability issues severity level as high, and the performance issues severity level as medium. As for reliability issues, we measure them by checking the criticality of the corresponding infrastructure operations. For the unreliable scripts which are related to the infrastructure critical, moderate, or trivial operations, we consider their severity levels as high, medium, or low, respectively. We come up with a real-world solution called SecureCode using our analysis platform to identify the risky scripts in Ansible infrastructure code. To support the programming paradigm in Ansible playbooks, which are written in YAML with Jinja 2 template rendering, we propose our own template parsers as well as reusing parsing functions in the Ansible Link tool to implement SecureCode. As shown in the figure, we integrate SecureCode with CI/CD pipeline deployed in IBM services using Traverse CI. We test SecureCode in 45 IBM services community GitHub repositories in the call for automation context, hosted by the IBM Continuous Engineering team. This figure shows the output of one of the detected issues by SecureCode. The risky code happens at line 24 in the Mantle YAML file, where a shell script is invoked. The risky pattern of undefined variables matches SureCheck Rule 2154 with the type of warning. SecureCode reports this issue containing security vulnerabilities with severity level as high. The statically unconfigured Ansible node variable allows a user to pass any value from a command line when the user executes the corresponding Ansible playbooks. Without runtime sanity checking, an unexperienced user may forcibly pass wrong values to the infrastructure code. Even worse, a malicious user can inject untrusted inputs to the infrastructure, compromising the system and stealing confidential information. In this example, Ansible node is used in a SQL command, which is vulnerable to SQL injection attacks. SecureCode identifies 3,535 issues in total from the 45 repositories, which contain 1,492 automation files. We manually investigate all issues and fill out the false positives. We find 116 issues are false positives. For the remaining 3,419 true positive issues, 1,691 have high severity levels, 298 have medium severity levels, and 1,430 have low severity levels. We use both the number of detected issues and the number of detected issues per line of code, we call it IPL ratio, to evaluate the code quality of each test repository. We observe that the issue numbers and IPL ratios tend to fluctuate utterly, ranging from 0 to 1,414 and 0 to 0.45, respectively. We believe that the variation of code quality are caused by different development experience, coding practice, and scripting language expertise. We have further designed quantified metrics to access the user experience from IBM Continuous Engineering team by comparing SecureCode with manual checking, vanilla SureCheck, and vanilla PS Script Analyzer in terms of the throughput improvement and efficiency gain. Secure Code achieves 2 to 5 times throughput improvement compared with other approaches. Secure Code can also identify 2 to 5 times more issues than other approaches. The user experience shows that Secure Code removes the bottleneck of code review and shortens the time to the market. To conclude, we take a first step towards the direction on identifying risky IAC embedded scripts by proposing an IAC embedded script analysis framework. The fundamental idea is to bridge the gap between generic state-of-the-practice script analysis and business consequences. We implement Secure Code on our analysis framework. Secure Code is accurate. It identifies 3,419 true issues with 116 false positives on 45 Ansible repositories. Secure Code is a roadmap in this journey. Additional features to be implemented are on our schedule, including supporting more scripting languages and supporting checking infrastructure code in other IAC tools. Thank you.